Greetings everyone, my name is Dhrukumar Vyas from Semester 3 pursuing BTech in Information and Communication Technology ICT at Marwar University. This demonstration video is my submission for the active learning assignment in the subject Introduction to Communication Engineering. This video is a follow-up video of my previous video where we explored transmission impairments in detail. Do check that video out if you haven't already. In this video, we'll be doing a signal processing activity in Python. Particularly, we'll be learning how to digitally remove noise from any noisy signal and get a filtered signal. This video is also related to digital signal processing DSP along with communication engineering. Without any further ado, let's get started. For this activity, we'll be using the PyCharm IDE. We'll start by importing all the necessary libraries. In this activity, we'll use the noisy signal from this noisy_signal.wav file, which is nothing but an audio file containing a noisy signal. We'll start by importing numpy as np. This will help us work with numpy arrays. We'll import matplotlib.pyplot as plt. This will help us with plotting graphs. Then we'll import scipy.io.wav file. This is a signal processing library in Python which will help us read data from this noisy_signal.wav file. Lastly, we'll import the scipy.signal as sig. This will provide us with the required filters for removing the noise. We'll start this activity by reading the data from the noisy_signal.wav file. To read the data from this noisy_signal.wav file, we'll use the .read method of scipy.io.wavefile library. As a parameter, we have passed a string, which is the path of the .wav file. This method returns two things. First is the sample rate of the WAV file, data type of which is an integer, and the second is the data, which is a numpy array containing the data read from the WAV file. We'll store the sample rate in sample_freq variable and the numpy array in data variable. Now we'll create the time axis using np.arrange method. We'll pass the length of the data and divide the whole thing by the sample frequency. We'll store this in the time_axis variable. We now have our data and time axis. We'll now create the main thing required for this practical, a filter. For creating a filter, we'll use the .butter method of signal module of scipy library. .butter method creates a Butterworth filter, which is a famous type of filter. In .butter method, we have passed these parameters. The first parameter defines the order of the filter, which is of integer data type. The order of the filter will decide how fast and steep the transition from the passband to stopband will occur. This is also known as roll-off. Here we have used a 10th order filter, so the roll-off is 200 dB per decade. Now by performing the spectral analysis of the noisy signal, I found that the noise in the signal is of high frequency, whereas our information signal is of low frequency. We'll see this for ourselves later in this video. So I have used a low pass filter which will allow low frequency data signal to pass and will attenuate or reject the high frequency noise. So I have used here B type is equal to low pass. This indicates that our Butterworth filter is low pass in nature. Next we have written analog equal to false. This indicates that our filter is a digital filter and not an analog filter. This 0.1 is the normalized cutoff frequency of the filter. Cutoff frequency is the frequency at which the signal attains -3 dB attenuation. As this is a digital filter, the cutoff frequency needs to be normalized between 0 and 1. We normalize the frequency by using the formula normalized frequency is equal to cutoff frequency divided by sampling frequency by 2. This is done to follow the Nyquist criterion. This output equal to BA is used because we want to return the numerator and denominator polynomials of the IIR filter. The numerator is stored in numerator_b variable and the denominator is stored in denominator_a variable. Now these moving window filtering methods often result in a filtered signal that lags behind the original data, that is, they create a phase shift. By filtering the signal twice in the opposite directions using the FILT method, it cancels out this phase shift to produce a filtered signal which is nicely aligned with the input data. We have stored the resultant filtered signal in filtered underscore data variable. Now we'll be creating four plots. The first plot will be the time domain representation of the noisy signal. Second plot will be the time domain representation of the filtered signal. The third plot will be the frequency domain representation of noisy signal, and the last fourth plot will be the frequency domain representation of the filtered signal. Now plotting a graph in Python is very easy, and I'm hoping that all the viewers know it. Also, it is very self-explanatory. So you can see the code for yourself.
To get the frequency spectrum of our signals, we have used the dot magnitude underscore spectrum method of the pyplot library. Now let's run the code. You can see that we have got four graphs. The first graph represents our original noisy signal in time domain. The second graph represents the filtered signal in the time domain. The third graph represents the noisy signal in frequency domain, and the fourth graph represents the filtered signal in frequency domain. You can see that our original signal, which is in orange color, is very noisy. If we look at the frequency spectrum of our noisy signal, we can see that there are some spikes in the high frequency side of the graph, and original signal frequency, whose amplitude is the highest, is at the low frequency side of the graph. Also, after filtering the noise from the noisy signal, the signal becomes very clean and smooth, as seen in the blue colored graph. When we look at the frequency spectrum of our filtered signal, then we can see that the high frequency spikes which were originally present in our signal have been removed. Now the frequency spectrum only consists of the desired frequency in the original signal. That's it for this video. I hope you liked this video and learned something new. I would like to thank Professor C.D. Parmar sir, HOD ICT department, for his thorough guidance in making this video. By making this video, I learned how to use noise filtering techniques that I had learned in communication engineering and apply them to make digital filters in Python. Thus, it helped me to migrate to digital signal processing. I also learned many new things regarding the Matplotlib and SciPy libraries. Thank you.